My name is Peter Baum and I'm a physicist at University Konstanz, Germany. My research is centered on the visualization of atoms and electrons in motion, and I'm very grateful to the Falling Walls Foundation for their awesome support. The fall of the Berlin Wall has been and is a very significant event to me. Besides its grand implications for my country and the world, the wall almost prevented my existence. If my grandfather with his two young daughters would not have fled from eastern to western Berlin just before the wall was built, my mother would not have given birth to the person you see here. Now about my research. I brought you here two unlikely objects: an original piece of the Berlin Wall and a calculator. As different as they look like, from a fundamental perspective, they are very alike. If you look deeply into all the matter around us, be it these objects, the air or the pixels in your computer device, they are all made of surprisingly simple ingredients, atoms and electrons. These simple building blocks make up all the awesome world around us and ourselves. And whenever something changes, be it a chemical reaction, computers at work, life, if you look deeply inside, simple atoms and electrons have to move from initial to final configurations. These motions are the reason behind almost any dynamics that we observe in our surroundings. Our research is centered around the question, can we make it visible and what will we see? We are facing two grand challenges here. Atoms are very tiny, but even worse, the motion from initial to final configuration are super fast and happen in merely femtoseconds and attoseconds. That is 10 to the minus 15 to 10 to the minus 18 seconds. It's a hardly believable short amount of time. An attosecond relates to a second like a second relates to the age of the universe. Yet in these tiny dimensions of space and time happen all the basic physics that defines the macroscopic properties of all the materials around us. How do we gain access here? We use an electron microscope, one of the most versatile instruments to see tiny things, and combine it with modern femtosecond and attosecond lasers. In particular, we use the optical cycles of laser light, which oscillate with a period of merely femtoseconds, to modulate the electron beam into pulses of similarly short duration. Two early electrons are decelerated and two late electrons are accelerated. In this way, the electrons catch up with each other and form ultra-short electron pulses that are now much shorter than the times we need to investigate. Like taking a sharp snapshot of disco dancers with flashes of light, we can now take sharp pictures of atoms and electrons in motion as a function of time. So in the end, we combine the awesome spatial resolution of the electron microscope with the awesome time resolution that is offered by the cycles of light. Currently, we are investigating, for example, electronic motions that lie beneath the wonders of nanophotonics, a research field in which tiny antennas are made smaller than the wavelength of light in order to create optical effects that are entirely not achievable with any natural material. Also, we are investigating how the atoms move around when we change the magnetization of a permanent magnet. It turns out that the atoms rapidly start circulating around their equilibrium positions, each on their own path. Only much later, the entire magnet starts its macroscopic rotation as demanded by the Einstein-de Haas effect. The atoms, and not the spins, are therefore providing the fundamental limit for the speed of magnetic changes. Our electron microscopy with laser control is a very versatile method. Almost any material can be excited with light, and almost any material can be put into an electron microscope. So we have now the capabilities to see atoms and electrons in motion in almost any process of relevance. For example, in material science, ultra-fast electronics, quantum physics, or maybe even biochemistry. Despite these advances, not all is clear yet. Some pressing questions remain to be resolved. For example, how short can our electron pulses actually become? Is attosecond really already the limit? How complex materials can still be investigated? Can the electron as an elementary particle become a useful object for quantum technology? What common principles are behind material transformations? Is there eventually some kind of periodic table for ultrafast dynamics? Not the least, can we make our instruments even simpler and cheaper for everyone to use? Stay with us, we will find out.